Today we are going to talk about duality in optimization. We had already said that we would talk about duality. So, let us just write down the topic of our discussion today. Duality is a vast topic, subject by itself as a part of optimization. There are lots and lots of studies devoted to duality. What duality says is that behind every minimization problem there is some maximization problem which is simultaneously going on, and there is a relation between the solution values of the original minimization problem and this dual problem which is going on at the back. So, the maximization problem which is going on at the back is usually known as the dual problem, and the original problem that you want to solve, the minimization problem that we are using here, is called the primal problem. Now, this issue of two problems are being handled simultaneously, though you are actually handling one problem at the back, automatically there is another problem getting tackled, is a issue of very big significance, because what would happen is that if the original problem is difficult to handle, it is in many cases, for example, in the case of linear programming, the dual problem is simpler to handle. An important issue is that are the solution values of the primal and dual problem equal? That is a very fundamental question which we will discuss. Of course, we do not have the course is coming towards an end, and we really do not have so much time to discuss duality in detail, otherwise the duality itself would be 10 or 12 lectures. So, because this is a foundational course, we are trying to pack in many things into it and trying to give you as much as rather some sort of a broad picture of the subject rather than going into details of everything. Now, this issue of duality is linked to what is called game 2% zero sum games. We will use this 2% idea of 2% zero sum games, a concept which was very well studied by von Neumann and Morgenstern in their famous book Game Theory and Economic Behavior. So, this 2% zero sum game means there are two people who are playing a game. So, there is a player 1 and there is a player 2. There is a player 1 and there is a player 2. Player 1 has a strategy set X, say in Rn, and we call, and this set let be is compact and convex or whatever, maybe compact is fine. And player 2 has a strategy set. For example, you are playing chess, you have your strategy set and the other person has their strategy set. Nobody knows what strategy you have. So, these strategies are not revealed to each other. These also assumed to be compact. So, player 1 can take an X belonging to X and make one move in the game, while corresponding to it player 2 can make a move by taking Y from Y, and whenever there is such a move having the strategy pairs X and Y, player 1 plays player 2 an amount kxy rupees, say. So, this is usually called the payoff of the game. Now, why payoff is there, why you need to define is a big issue. I would rather, for those who would like to go more into games, it would be very beneficial if you look into this book. This is a fabulous book on game theory. my favorite actually, that is why I also want to share with you. That tells you why you need a payoff, how do you design a payoff. So, there is a lot of issues of designing payoffs and all those things. So, they has issues related with economics, which is pretty interesting by the way, but let us just take that okay, he is making a, now it does not mean that every time this guy player 1 is giving player 2 money. Okay, if he is giving money player 1 to player 2, then kxy is positive. If he is receiving money, then kx is, if he is giving money, then kxy is negative for is positive. So, he is giving away money, and when he is receiving money it is negative. Rather, when kx because he receives money player 2, it is positive for him, and if he gives away money it is negative for him. So, that is the way it is. So, every time this amount, certain amount is been given, and so whatever is his gain is his loss. So, the total payoff, the total gain of the players is actually 0. So, that is why it is called a zero sum game, right. So, if y is receiving kxy amount of money, then if player 2 is receiving kxy amount of money, then player 1 is losing kxy amount of money. Now, let us look into what the way player 1 and player 2 would actually think when they are playing the game. Now, player 1 knows that he has to pay some money kxy. So, he wants to know that if he pushes this strategy x, if he plays on a strategy x, he has no idea what strategy from y would be known. So, the strategies are not revealed beforehand what I will play. So, for the time being, let us know that both of them know their strategy sets. For example, when you play chess, you know that okay, both if you are, suppose you are super experts, then you would know that okay, these are the only possible moves you can make in the game. So, in that way both possibly know the strategy sets, both could be x actually, that is a different thing. So, here just for generalization we are writing x and y and all these things. Now, given this strategy x, once he had played x, he has no idea what move y the player 2 is going to give. It could be any y in the set capital Y. So, in that way, so he wants to know what is his maximum loss, which is very natural. If I am also playing, I want to know okay, if I play x, what is my maximum loss. So, I want to maximize obviously y would like to, player 2 would like to put a move which would take as much money as he can from player 1. So, player 2 would like to make a move, so that as much as money he can draw from player 1 he would like to take. So, player 1 wants to know beforehand what is the maximum loss he can have, what is the maximum loss of money he can have once he has played the strategy x, which means if I call this as phi x. So, for every player, every move x in x, he is noting the maximum loss. So, anyone who try to minimize this maximum loss, if I am anyone is player 1, his natural idea would be to play an x for which this is minimum. So, this is your minimization problem. So, player 1 is actually solving a minimization problem. So, kxy of course is a function of x and y, which gives you a real number because it is rupees. Now, this is what player 1 is playing. Let us look at what player 2 is thinking. So, player 2, now suppose he has given a strategy y and he does not know, for example, corresponding to his strategy y, what move the player X is going to make. He only knows that player X, so once he has made his move Y, he obviously does not know what move the player 1 is going to make. Now, player 1 can move any move X from his set X. The important part is that this guy obviously knows that he is going to get a money kxy amount for every X he moves, but he also believes that he does not know what, he also wants to know what is the minimum amount he can extract from player 1. So, he would like to see for a given y what is the minimum amount of money or the minimum amount of profit he can make from player 1. So, this is the minimum amount of profit that player 2 is going to make. So, if I am player 2, I would like to maximize that minimum profit, everybody would like to maximize profit. So, I would like to maximize phi y. You can of course write this is player 2's problem. So, player 2, as player 1 is solving a minimization problem, player 2 solves this maximization problem. Technically, you can say that okay, I can write this whole problem as mean of max of this and this as max of mean of this. Of course, you can do that. The question is now, when are these two values equal? If these two values are equal, then the x for which this value is equal to this and the y for which this value is equal to this is the optimal strategy of the players. That is, if I deviate from that strategy, neither of us are better off. So, the very important question is, when is these two values equal, under what condition on k possibly, what should be the behavior of k which will make these two values equal. So, this is your, so the player 1 plays the primal problem and player 2 plays the dual problem. Now, when it comes to the standard mathematical programming problem which we had been writing as P, that is to minimize fx subject to now, can you design something like this? Is this problem can it be represented as a mean max problem, mean of max of some function depending on two variables? Can it be written like that? Is it possible? That is the fundamental question. Basically, you are trying to imitate this whole process that we have described just now for a standard mathematical programming problem. Now, the question is, if that is so, if you want to do so, you want to know what it would be your payoff function, what is the analog of kxy that you know for the games, what is the analog for the mathematical programming problem. Here the analog is the Lagrangian function, which is written as fx plus now this, in this case, lambda is in Rm plus and this is in Rp, x of course is in Rn. Now, this is the standard Lagrangian function which we already know. Now, can I write this original problem as max of Lx lambda mu over mean of something? Okay. Let us see what would happen if I want to. So, in this case lambda and mu are assumed to be the strategies of the player 1, the original problem, and so here let me see what would happen if I do this. So, varying lambda mu over Rm plus and Rp, Rm plus cross Rp, let us see what would happen to this. Now, let me call the feasible set of this problem P, feasible set as C, which consists of all x which satisfies Gix less than equal to 0 for every I and Hgx equal to 0 for every j from 1 to P. So, now once you know that C is a feasible set, now consider an x in C, then of course all the Hgx is equal to 0, Gix's are less than equal to 0. So, then whole of the thing, this whole Lagrangian, when you are taking x is in C, then the Lagrangian for any lambda mu you choose in this set, that is less than equal to fx. But if you choose lambda and mu both to be 0 0 vectors, then that is exactly equal to fx. So, the supremum of maximum, or the supremum I would say, because you cannot use the word maximum in that sense, but you can use the word supremum. Here I use the word maximum or minimum because I know these are compact and assuming that these are continuously nice continuous functions. So, here this is fx if x is in C. So, what is the answer if x is not in C? So, if x is not in C, the supremum blows up, it is plus infinity. So, how it is plus infinity? If x is not in C, there means either there is an hx x, there is a j for which hjx is not equal to 0, or a I, or both in fact, or a I for which gix is strictly bigger than 0, or both. So, suppose I just take the one of the cases for which hjx, take an x for which hjx is not equal to 0. So, and without loss of generality assume hjx is positive. So, make all the lambda mu's to be 0 and keeping the mu associated with that particular hj, that is mu j, to be positive. Now, you keep on increasing the mu j as much as you want. Then moving along that mu j, as you increase mu j, the value of the Lagrangian function will keep on increasing and it will not decrease, and I can so blow up the value, and that is why you have this. Now, this is slightly different from the look of this. So, if x is in C, you will get this, if this is this, you will get this. This is a structure, this can also be written as something else. This is a structure which is used very often in modern optimization, which is actually borrowed from this sort of way of writing the original problem P, representing the original problem P. So, if you want to minimize a function fx over a set x element of C, which is a constant problem, you can convert this constant problem to an unconstant problem. You see, you have actually now what I have to do is to take the minimum. So, the original problem now is to take the minimum or infimum if you want to write. So, my original problem P is can be now represented like this. So, whenever x is element of C, this is f x, or else it is plus infinity. So, in many, so this problem can now be written the same structure can be written put in a much simpler form, that I can now write this whole problem as minimize x, minimize f naught x where x is in Rn, where f naught x is f x when x is element of C and is plus infinity when x is not element of C. So, this is basically I am putting infinite penalty for not maintaining feasibility, and that this conversion of a minimization problem of a finite valued function over a set C can be converted into the minimization of an extended real valued function over the whole of Rn, and this structure is the hallmark of modern optimization, and it actually comes from this formalism, this way of writing the original problem in terms of the Lagrangian function. So, this is my player 1's problem. So, how do you write the player 2's problem? That is the whole question. So, the original problem can be written like this. So, could it be that I can change these two? Okay. So, my dual problem, so if my primal problem P is say inf of maybe maybe we become more erudite and write so if this is my original primal problem P, is my dual problem can be done by swapping these two, that is soup of in fact, indeed, if that was a player 1's problem, the primal problem, this is indeed the dual problem. So, the dual objective function which is phi x, phi y in the game now can be written as theta lambda mu, which is infimum So, this is called the dual objective function or the dual function. Now, the question is why is the dual problem important? Okay, fine, you have found that there is another problem which is going on at the back of the primal problem, and then but so what? So what is this? Now, consider any lambda, fix up my lambda and mu. Where lambda mu belongs to and then consider this function. By definition, for whatever x you take, this is now suppose this is true for all x. Consider any x in C, consider x to be in C. Then theta lambda mu is less than equal to f x. So, so if this is my dual function, then the dual feasible set is this Rm plus cross Rp, this is a dual feasible set. Now, here you see what we have done is that we are asking what would happen if x is in C, but when x is in C, h of hgx is 0, lambda I gix is less than equal to 0. So, finally, that whole thing is less than fx. So, for any pair from the dual feasible set lambda mu is taken and any x from C is taken, this is always holding. So, this result is called the weak duality. Now, this can be posed in a better way. Now, what does it tell you is the maximum of theta lambda mu. So, if this is holding for theta lambda mu for every lambda mu, if I fix the x, then this whole thing would be less than equal to fx for a fixed x, where lambda mu belongs to now. Once this is done, this is true for whatever x you choose fix up. So, which means I can again take an infimum of the x's, which is my primal problem over C, and I will get this relation. So, this is a consequence of the weak duality inequality. So, this is sometimes also called the weak duality, either this or this, whatever you want to call, because this is the same as this, and this implies this. Now, once this is known, this weak duality is known, the question is when will there be equality. So, when if equality holds, that would result into what is called strong duality. So, strong duality is something what we need, but before we go in and discuss more about strong duality, we would like to get into some examples, etc., and we will start with some features of the dual function itself. But these features, some of these features would be given to you as homework. Theta lambda mu is a convex function for lambda mu, sorry, concave, not convex, I made a mistake, concave function. Please correct this, it is a concave function. I should have written minus lambda mu. So, what you are doing, you are maximizing a concave function, or in the same sense minimizing a convex function. So, every local maximum of the concave function is a global maximum, and hence the dual problem, this problem D, is a convex programming problem. So, this problem is a convex programming problem. Now, so here comes the first advantage of duality. Now, this is something, this thing you take it as a homework, HW is shorthand for homework as always. Now, what I want to stress is that here comes the first advantage of thinking about the dual problem, by taking the dual problem into account, is that we have a convex optimization problem which is actually solving, whose solution actually provides to me the lower bound to the solution of the original problem. So, if I can solve, because convex optimization problems have well known good solution methods, if I can solve the dual problem and get a finite value as the solution, then I know that my original problem cannot have a minimum value beyond this. If I immediately know my original problem has a solution, and if my original problem now has a nicer structure like a quadratic programming problem over a polyhedral set, then I immediately know that there would be a minimizer existing for that. So, these sort of advantages can be obtained by looking at the dual problem. But the dual problem has one major disadvantage. The major disadvantage is as follows. This is not differentiable at every point. See, this is very important to know that this is not differentiable, because you are basically minimizing. How do you write down this one? So, once you fix x in terms of lambda and mu, this is a linear function or affine function actually, if there is a added fx. So, this is an affine function. So, you are taking the minimum of a family of affine functions. You are taking a minimum because each affine is convex. So, you are concave. So, both convex and concave actually. So, you are taking the minimum of this, and what you are getting out is a concave function. So, here for every fixed x in terms of lambda and mu, this is a linear function, and now as you vary this index x, that is you are making, so that x is generating the family of concave functions. When you take the infimum, you will get a concave function. So, this is a concave function. Now, this non-differentiability might turn out to be problematic. So, first we will write down few examples which as a homework you should learn how to construct the dual problem. Once you learn to construct the dual problem, you will generate more confidence in the show of duality. After we write them down, we go ahead and we describe a problem from the geometry you can see that the equality of these values are guaranteed. Equality of these values are guaranteed. So, let us just write down the problems that I want to give you as homework. So, let me start with this problem. So, take the linear programming problem LP, where you minimize a linear function over affine constraints. Sorry, maybe I will put AJ. So, C is in Rn and AJs are in Rn. So, Bj's is in R. So, now can you write down so the next problem is a quadratic programming problem, where I replace the linear function by a quadratic function with a Hessian matrix Q, and which is positive semi definite. Subject to the same constraints. Of course, I will give you these calculations in the FAQs. So, those who will not be able to calculate them out, we will calculate them for you. So, you need to look at the FAQs. So, write down the write down the dual problem. So, homework is to write down the dual problem, write down the dual of the following problems. So, this dual is sometimes called the Lagrangian dual because you are using the Lagrangian function. So, now we shall show through an example how the very geometry can show you that duality actually exists, strong duality. See what happens if you just have equality constraints, then your dual problem, that is taking the supremum of this, supremum is only taken over mu. So, then your dual problem actually becomes an unconstant problem, which is a very big advantage actually. We will also show, if time does not permit today, then tomorrow, then that I will show a case where the dual function is differentiable, and I will show a case the dual problem is non-differentiable. Whenever we have the dual function written like this, does not always mean that the dual function would be non-differentiable, but in general it is non-differentiable. For example, I will just give you a function. So, for example, if you take phi x is max of x square and 0, this is differentiable, but if you take phi x as max of x and 0, this is not differentiable. So, this is differentiable and this is not differentiable. So, theta lambda mu written like this does not tell you that that is differentiable and that is always non-differentiable. It could be differentiable, it could be non-differentiable. Okay. So, now let me just try to write down a result, rather a problem, and the very basic problem, the projection problem, and let us see what you get out of it. So, you are fixing up a point z, take a point z, and take a matrix A, say n cross n matrix, to be very simple. You can take m cross n matrix also, but let us just take n cross n matrix if you want, or if you are comfortable with m cross n, we will go for m cross n. Okay. So, I am looking for the projection problem, that is I am trying to find the distance between z where x belongs to kernel of A, where A is a m cross n matrix. So, this problem can be written as, so it is a convex programming problem, of course, because this is a convex. So, geometrically Ax equal to 0 is a subspace in Rn. The set of all x which satisfies Ax equal to 0 is a subspace of Rn, and you already know that kernel is a subspace, and the subspace has to pass through 0. Suppose for the time being that this is the line Ax equal to 0, I am just explaining you in 2 dimension. Now, what would happen if I try to write down the dual of this problem? The dual of this problem means we have to write down the Lagrangian, right. Which is half of, see this z is fixed. So, z is fixed, it is from z we are trying to find the, so basically there is a fixed z here and we want to know the distance of z from this, that is find a point on x on Ax equal to 0 which is nearest to z. Basically you drop a perpendicular from z to Ax and geometrically find what is that point where the perpendicular will hit the line Ax equal to 0. Actually, when it will be in this sort of thing, it will be just Ax equal to 0, that is just A1 x1 plus A2 x2 equal to 0. But here I am just writing Ax equal to 0 to keep the general flavor. This plus mu times Ax, Hx basically. So, mu I am not writing summation mu I am just writing it like this because if I write each one of them as A1 x, A2 x, A3 x, then I write mu 1 A1 x, mu 2 A2 x. So, I am just writing it in a more compact form. I think this amount of mathematical maturity you should have towards the end of this course. So, now if I want to find the dual problem, I want to construct theta mu. So, which means that I need to minimize Lx mu over x element of Rn. But this is a convex optimization problem, this is a convex problem. Why? Because you can write, once you have fixed the mu, for fixed mu, Lx mu is half of can be written as, so in x it is a convex function, and for a convex function every critical point is a global minimum. Now, then if I differentiate this, right, and equate it to 0, so x would be equal to minus, so solution of this problem, say x hat, would be equal to minus A transpose mu. Not really, sorry, I am making a mistake. It should be, sorry, it should be, if I differentiate, then it will become x minus z plus A transpose, sorry, mu equal to 0. So, this is x hat. So, if I differentiate it, this is the derivative, I am equating it to 0, and the x for which this derivative would be equal to 0, but this would be equal to 0, the x hat. For that x hat, that x hat is the minimizer of this problem basically. So, which means x hat is now can be written as z minus A transpose mu. So, my theta lambda mu, sorry, theta not lambda mu, theta mu, because there is no lambda, theta mu is now minimizer of this. So, how do I express that minimum? So, the minimum value is putting this in place of x. So, half of z minus A transpose mu minus z whole square plus A transpose mu into z minus A transpose mu. So, the origin now, which means that the original problem, now the dual problem of this can be written as maximize over mu, which is the unconstant problem. So, it can be written as maximize over mu. So, now if I do some manipulations here, because z would cancel, so and you will have A transpose mu norm square from here also. So, that would give you minus half norm A transpose mu whole square plus A transpose mu z or mu A z. So, this is, now I have to maximize this over mu. Okay. fine. Now, I can add a half norm z square to complete the square, and then I can write this as, so this is equivalent to same as writing as, basically you add plus half norm z square and put minus half norm z square. So, you will have max of over mu, mu is in of course Rm. So, if you are not sure, then let me write for you, mu is in Rm, and this is what I will get as norm A transpose mu minus z whole square plus half norm z whole square. So, what is this measuring? So, if I take all the mu's in Rm, then A transpose mu is nothing but the image space. A transpose mu is nothing but the image space of A transpose. So, which is actually orthogonal to the subspace Ax equal to 0, to the kernel of the A. So, you know image space, this is image of A transpose, this is basic linear algebra, is the orthogonal complement to kernel of A. So, with using that idea, this is nothing but you are minimizing the distance of z from this thing A transpose mu. So, basically you drop here, you want this. So, find a mu hat such that A transpose mu hat would minimize this. So, this is my A transpose mu hat position, and then corresponding to this, as you know, for the convex case, this is a closed convex set, there would be an x hat, there would be a projection. Let this be the projection on x hat. Then what does it show? This distance is A transpose mu and this distance is x hat. So, this distance is x hat minus z square, and this distance is z minus A transpose mu. So, what is happening is, if you look at this distance, this is z minus A transpose mu. So, basically you will have, finally you will have z minus A transpose mu, mu hat, this distance square of this plus square of this is nothing but by Pythagoras theorem the norm of this whole square. So, here is my mu hat where the perpendicular lands, here it lands at x hat. So, you see now this plus x hat, sorry, z minus x hat is equal to norm z square. So, finally what I get from here is half of norm x hat minus z square is minus half of norm A transpose mu hat minus z whole square plus half norm z square. So, mu hat is the solution to the dual problem, mu hat is the solution to this problem. So, the solution to this problem is mu hat and solution to this problem is x hat. So, this is the maximum value of the dual problem and this is the minimum value of the primal problem, and they are equal. Here you see we had not put any additional things on the constraint, which gives us a fact that if I have linear or affine constraints for a convex programming problem, possibly the strong duality always holds? The answer is yes, which we will discuss in the coming 2-3 classes. We will give more examples and we will discuss in more detail the basics of strong duality and its applications to certain interesting classes of problems. Thank you very much.